Hi, my name is Patrick, and for assignment 2, I picked the two symbolic tags, unconditioned generation and condition generation. Both are on the same dataset and both uses the same model architecture. And that's intentional, and I'll explain why in a second. And in this presentation, I'll walk through the data, the model, the training setup, and the evaluation. And at the end, I'll play the two generated MIDI files that I'm submitting. So the data set that I use is NES music database, and it is released by Chris Donaway. It has roughly 5,000 songs from 400 NES games. What's special about this dataset is that it is parsed directly from the assembly source of the game, so each song captures the exact register level synthesizer state at sample accurate timing. So it's much cleaner than transcribing emulator audio. And the audio processing unit has 5 voices, and it exposes NES MDB exposes 4 pitches. Pause 1 is typically the lead, pause 2 is harmony, triangle is the bass, and noise is the percussion. Out of all the format that they offer, I use the separated score format. It's 24 hertz piano roll, n by 4 array of pitches, where 0 means the rest. That throws away the velocity and timbre information, which I'm fine with, because I wanted to do the model composition and not performance. And dropping that information significantly reduced our vocabulary to just under 130 tokens. And here's the exploratory analysis. These are the basic statistics. It has about 4,500 training songs, and I think the mean is 32 seconds. So each audio average about 32 seconds, and it has a total of 2,400 minutes, roughly about 40 hours in total. And here's a length distribution. Most songs are between 15 to 60 seconds, and there are longer ones up to several minutes, but the median is around 22 seconds, which is not too bad. And here's the per channel pitch histograms, and pause 1 and pause 2 occupy the same range, from MIDI 33 to 108. Triangles is wider, it goes all the way down to MIDI 21, which is in the bass range. And the noise channel only uses 16 distance values because it's encoded as drum codes rather than pitches. And one thing I wanted to point out is notice how pause 1 and pause 2 are essentially mirror images of each other, but they're used at different intensities. So it's basically lead versus harmony row split showing up in the data. And this is the per frame voice activity. Most frames have two or three voices sounding at the same time. And the silence, zero voice is very rare. I'd say about under 5%. And the model needs to relearn this density, otherwise it will either overrest or core stack on every frame. Here's a page class plot. The chroma distribution per voice across the whole training set. And as you can see here, C, G, A, and E dominate, and it's consistent with a core pass. That's mostly in major or minor keys with VI candidates. We'll use these chroma profiles later as reference distributions for kill divergence metric in the evaluation. And here is modeling. Both tasks use the same casual transformer, and the only thing that changes between task A and task B is a loss mask. Each song becomes a flat token sequence of length 4 times n, So for each frame, it emits four tokens in fixed channel order, P1, P2, TR, and O. And the model learns the next token prediction with cross entropy, factoring the full joint distribution as the product of conditionals. So for task A, the hand condition task, I compute the loss on all positions. And for task B, the condition task, I compute the loss only on positions whose channel isn't P1. So the model still see the melody, and those tokens are in the context, but it's only graded on prediction harmony, bass, and drums. At sampling time, I feed the model a targeted melody, and every time we hit the P1 position, I would override with whatever the model sample with the ground truth pitch. This is much cleaner than building a separate encoder decoder model because both tasks share the same parameter count and same data pipeline. And any difference in evaluation results comes from the conditioning itself and not from the confound. And the architecture is a standard small decoder only transformer with 8 layers, the model 512, and it has 8 attention heads. And um, I tied the input output token embedding and choose absolute position embedding, and also added a small channel embedding index by position mod 4, so the model knows which voice each token belongs to without having to learn that pattern. And it has about 26 million parameters in total. The trade-off is that with about 14 million training tokens and a model this size we're slightly under parameterized, which is what we want because it means the model can just memorize the training songs. And I chose the 8-layer 512 dimension because anything bigger and the validation loss curve started flattening. Anything smaller and the model couldn't capture the inter-channel coordination. And here's the training. So for both runs, it uses Atom W with these parameters, and each run takes about 20 minutes on my 5070 GPU. Here is the training curve. Uh, Val loss converges to 0.45 on task A and 0.41 on task B. And perplexity is over 1.56 over the vocabulary of 130. But for task B, it's marginally lower at 1.52. It is because the condition model is predicting only three of every four positions, with the easiest one, the melody. Uh, so the train loss is consistently lower than the val loss because we use dropout in training but evaluate without it, and that gap is expected. And here's the evaluation. So the question is the model any good? So for symbolic music, there is no single ground truth. Many different sequences are equally musical, so I report a small suite of complementary metrics, each catching a different failure mode. Uh, perplexity, uh, perplexity is a model what uh, uh, is what the model is actually optimizing, but low perplexity doesn't mean good musical quality because model that always picks the most common note will have great per token likelihood and be very boring. So I also report pitch class scale divergence against the training, which measures whether we're using the right notes, and voice activity per channel, self repetition fraction, and anti frame fraction. Self repetition is interesting because both extremes are bad, Zero repetition means that the model is producing noise. Very high repetition means it's stuck on the single chord. So the training area sits around 30 to 50% because chiptune is rhythmic and loop driven. So we wanted to generate it samples in that range. And here's the baselines. There are three unconditional baselines: uniform, random, per channel, unigram, and per channel bigram. For condition text, there are four. There's a fourth, which is a nearest neighbor retrieval. Given a melody, find a training song whose melody has the closest pitch class profile and copy its accompaniment. These baseline are not just sanity checks. The bigram baseline is particularly is a strong comparison because it captures local pitch transitions much better than the unigram. If our model can't beat the bigram on pitch class scale, something is wrong. And here are the perplexity numbers. Wait, hold on. Yeah, here are the perplexity models. Numbers, I mean. So it's 1.47 for text A and 1.43 for text B. Uh, so we're modeling the distribution well, and I think the conditional model is slightly better because it doesn't have to predict the melody. And yeah, so here's a good interesting comparison. You can read from the row top to the bottom. It has real test data, uniform, unigram, bigram, and our transformer. You can look at the self repetition, and that's a column from second from the left. Real chiptune is about 0.74, which is high because chiptune is loop driven. The memory less baseline is at 0 dot, and bigram lands at 0.44, which captures some local structure, but it flips too quickly. Our transformer is at 0.74. It's almost exactly matching this real distribution. And yeah, the for task B, the condition, here is the metric table, and we compare with the ground truth and the nearest neighbor retrieval baseline and our model. All conditioned on the same held out task melody. And voice activity on P1 is identical across three, and that override mechanism is working. And the best voice TR is closest to real with our model ahead of NN. Where we have a weakness is pause to activity. We leave it silent more often than real songs do. So I flagged that in the notebooks limitation section. And self repetition on the transformer matches the real distribution at 0.75. This indicates that the model is reducing structure and loops accompaniment. Here are the generated samples. These two are the files that I'll be submitting. The condition one is generated from scratch, 30 minutes long, and the condition one is also 30-second long with P1 melody taken from the held out test songs that the model has never seen during the training. And here are the piano rolls. Um, Wait. Here are the piano rolls. You can see four channels are used with appropriate row separation. The lead voices are in the upper range, triangle hanging out in the bass, and noise sprinkle in for percussion. This is side by side for the condition example right here. The original accompaniment that one with this melody versus what our model actually wrote. they're different, and there's no reason why they should be the same. But you can see that the model has picked a similar harmonic register and rhythm density. Before I play the music and end my presentation, and here's a related work. Yeah, let's first hear the end condition. Okay, that should be enough. And here's the condition one. And here's the real next song. And here's our condition model on the same melody. Okay, so that would be the end of my presentation. I hope you enjoyed it, and thanks for watching.